Come sapete questa presentazione è in inglese, quindi giusto per tenervi svegli adesso switchiamo. So I am very pleased to be here again. Maybe some of you remember a couple of years ago we did the presentation on the launch of MTG-I, so the imager of the third generation. Now, after all the phase of commissioning, we are ready, actually the day after tomorrow, to use this satellite as a prime imager for European missions. And since we never get, let's say, bored in Humidity, we are also launching the next satellite in just about 2 weeks. So this is the MTG-S mission, is the sounder, of which my colleagues Enrique and Claudia will talk to you about. A couple of words about them. So Enrique Hortas is basically is our spacecraft operation manager for the MTG-S satellite. Units that we call that role operation team leader. And Claudia is basically our mission specialist. She is the expert on the IRS, which is the main instrument of this mission. Enrique joined us in 2019. Since then, he has been first working on the second generation satellite, this satellite here, and more recently he moved into the role of MTG-S operation preparation, because he followed all the phase of the preparation of the satellite, and now he will be in charge of the routine operation from next month, so no holiday this year. And before that he was working for 11 years at the DLR, where he was working on GEO and LEO missions and also did a number of LEOPS. About Claudia is an astronautical engineer, and she has about 15 years of experience on many projects with the Humidity and of course ESA as well. She also worked with me on the second generation satellites, and now, as I said before, she is our payload expert on MTG-S. So I will leave them the floor, and thank you.
So, good afternoon, everybody. First of all, I would like to apologize because I believe I'm one of the reasons why this has to be in English. So, sorry for that. It's me. But yeah, thank you, Flavio. Thank you, Michaela. Closer. Oh. Okay. So, thank you, Flavio. Thank you, Michaela. Thank you, the consulate. So, for this opportunity to have a talk about MTG-S mission. So, it's always difficult to prepare a presentation for general people. So, we have children, we have outsiders. As you mentioned before, we have experts like Mr. Henry. I don't know, I can see him now. So it's very difficult to put a few slides that make sense to everybody. We try our best, so don't worry, there is a bit of introduction, there's a lot of technical stuff as well, so we try to keep a bit of everything on the presentation. So let's hope it works. Yes, so the agenda, so we'll give a bit of introduction to Meteosat, what we are, since when we are there, etc. We go to the third generation of the standard, and then we get to the meat of the presentation, the star of the spacecraft, which is the IRS instrument, where Claudia will give us some inside information. Introduction to Meteosat mission. So this is the very first weather satellite. It was launched by NASA in the 60s, so it was called TIROS-1. It was a LEO orbit. So low Earth orbit, around 400, 500 kilometers away from the Earth, not far enough from biomass is. So yeah, and it delivered the very first image of the Earth from space. In a few years, ever since, now we have from that small picture to this. This is an animation of images from the MTG-I1, as Flavio mentioned before. So the last image here that we launched 2 years ago, and it's now operational. This is an image from the Canary Islands, and we can see, of course, the level of detail is you cannot compare it to what it was before, and also the repetition, the number of images we have. So it's very smooth, the transitions, and we can create an image we get an image every 15 minutes, so it helps a lot. Okay, so from when we went from that to what we have now. Outsiders, what is a geostationary satellite? Okay, so geostationary is a satellite which is 36,000 kilometers away from the Earth. That's an orbit that allows the spacecraft to be always on top of the same position of the Earth, so it's turning together with the Earth. Okay, so in Meteosat, in EUMETSAT, what we have on core satellites over Europe, and we monitor weather over Europe. But what can we see from a geostationary satellite? So we can see, of course, storms. So the first animation, whenever a storm starts, we see big clouds, we see big concentration of water vapors, etc. We can see volcanic ash. If there is a volcanic eruption, there is a concentration of aerosols, we can detect that from geostationary. With this precipitation, rain, dust, aerosols again, fire. In case there are some fires, we can monitor them, and everything. Again, the advantage of geostationary orbit is we can see constantly the same point on the Earth, so we can constantly see the evolution of the storm, the fire, or the dust. It's been 40 years of Meteosat, and I'd like to keep at least one word for every slide. So this one is 2 words: weather and climate. Okay, weather is something now. We can monitor weather with the spacecraft that we have with MTG-1 now, with the Meteosat second generation. On top of that, thanks to the 40+ years of Meteosat operations, we can study the climate because we have a backlog of images, data, information that helps not us with their operations, but experts on climate change, how the climate is evolving. Okay, so we started with the first generation back in '77, the second generation that's still delivering good data, so we still have 3 spacecraft of the second generation, and now is coming the third generation. Okay, so the current fleet, that's on the bottom of the slide, we have 2 spacecraft over Europe co-located at 0 degrees. So this is MTG-1 and Meteosat 10, both are the primary spacecraft. So Meteosat 10 was the primary up until now, and today it will be MTG-1. We have Meteosat 11, which is not far away, 9.5 east, and then we have a third spacecraft, second generation, over the Indian Ocean that helps us get a better coverage of the Earth. I mentioned we still have 2 spacecraft delivering data on the second generation, so just a few words. Most of you, if you attended previous presentations on the second generation, is a spinning spacecraft. It's delivering a full image of the Earth disk every 15 minutes, or an image of Europe every 5 minutes. This is old spacecraft, these are the new spacecraft. We have the third generation coming up. How it will look like in our configuration is we will have co-located all 3 spacecraft exactly at the 0 degrees. Of course, there is some safety measurements and they will be apart from each other, but we will have to manage them by dynamics. We'll manage them and make sure that they are apart enough, but they will be a bit more complex than only with 1 in the same location. We will have 3, but it's, we will manage for sure. This is introduction to Meteosat. Now we come to the third generation, so to the sounder. Some facts about the spacecraft. Okay? It's a geostationary spacecraft. It's a 3.5 tons spacecraft, 2 solar panels for the stability. It has some gyroscopes, so to help us measure the rotation of the spacecraft. We can compensate the attitude with the reaction wheels. So we have 5 reaction wheels, which are big wheels that are spinning inside the spacecraft to help maintain the position. We expect a lifetime, so we have propellant on board to last something around 10 years plus, depending of course on the number of anomalies and the good work we do. But we are confident that we will be beyond the 10 years. We have, of course, a power subsystems, as was mentioned before, biomass. We have solar panels that deliver power for all the electronic devices on board. In the orbital position, so as Flavio mentioned, we will launch in 2 weeks. The position will be 3.4 west at the beginning for the commissioning phase, and then we will move to 0 degrees in 1 year, give or take. So just another 3-axis stabilized spacecraft? No, it has a bit more. So it has some very special operations. Okay. Station keeping maneuver is a standard one, but we have something called the yaw flick maneuver. Okay, so what we do with the spacecraft is we turn. So if the Earth is there, we turn the spacecraft upside down. Okay, we do that using the reaction wheels. This is quite a critical operation. It's not something that we do every day in geostationary orbit, so it's quite, special operations. We have rotation maneuvers. We know that we will not always stay over the 0-degree position. We have the capability of rotate the spacecraft and move it in the ocean, for instance, if we want to provide further input in the Indian Ocean. Okay? So we have the collision avoidance maneuver. I mean, we are not biomass, so we are far away, but we still have some space debris over there. So we have the capability of, if flight dynamics reports that there is a high probability risk of having some space debris on our trajectory, then we will maneuver and we will maneuver and escape from that. We have the sun avoidance operations that is included on the IRS part, so we will have a bit more information on that one. And we have, of course, the end-of-life activities. Different from the LEO orbit, from biomass, so when the propellant is over on board the geostationary, we have to do a series of operations to leave the orbit safe for other spacecraft. Okay, they're so-called end-of-life activities. Basically, what it consists on going a bit farther away of the geo orbit and switching off the spacecraft. Sounds easy, it's complex. Yet again, another 3-axis stabilized spacecraft with some special operations. What makes the third generation sounder different and special are the instruments. So the both instruments we have on board, this is what makes really the difference on the sounder. So we have the IRS. With it, I don't want to make a mistake, numerical weather prediction covered by the IRS instrument, which is a hyperspectral infrared sounding mission. Okay. It's infrared, so we have the band of the infrared, but we will cover the whole band of the infrared. We don't have only few bands, but we have the whole. We will have every 30 minutes, we will have we'll go over Europe, and we'll have some information over Europe. Again, remember, so one word per slide, so in this slide it should be the vertical structure, which is what IRS will bring in-game. Okay, so we'll be able to see for the first time, not just the cloud from above, but we'll be able to see the whole vertical structure of the clouds. Not only IRS is on board, we also have the UBN. The UBN, I have a couple of slides later on, so it's a Copernicus mission, it's a Sentinel-4 instrument, and it will provide information about ozone, SO2, NO2, and aerosols over Europe. Okay? So, all in all, the MTG sounder will bring to Europe a faster, higher resolving, and more data to be able to identify extreme weather events. Okay, so eventually, we will all benefit from our good work, hopefully. So, synergy. I mentioned we have two main instruments, the IRS and the Sentinel-4. So the Sentinel-4 is a UVM, so ultraviolet, visible, and near infrared sounder. Okay, so it will be the first over Europe to monitor the air quality over Europe, and it will complement the IRS. So if you see on the table, so we have the bands of O3 and CO2 will monitor basically by the IRS instrument. With the UVM, we'll complement those and have also other bands being monitored. Okay, and it will only scan the Europe part, the UVM instrument. So why do we need to monitor atmospheric chemistry? Okay, it's for health, the air quality. We'll monitor gases O3, SO2, NO2, the UV radiation, the ozone in the stratosphere. We all know that we need it. Also, the ozone at the Earth level is not that good, so we will monitor that. For aviation, so we'll have a better overview of after volcanic eruptions, whether acid is injected on the atmosphere or not, where it's safe to fly over subregions. And of course, some time, yes, for climate change. So most of the gases that we will monitor are greenhouse gases. I think it's on all our benefit that we have as much information as possible over those. So I made a small introduction. So Meteosat, sounder, third generation, and now we come to the IRS. Yes.
Yes. Yeah, it's okay. This moment. Yes. So as you mentioned, the IRS is the infrared sounder, and it is the first sounder flying on a geostationary satellite. So this is probably the most exceptional thing, because we have other sounders that are flying on low orbit satellites, but this is the first on a geostationary orbit, so we are talking about 36,000 kilometers away, and this is also the reason why the impact that we expect on climate and meteorological products is so high due to the enhanced visibility that this will bring. This is what the IRS looks like. I have to apologize for this slide. But this kind of already brings you a taste of the complexity of the instrument. We can see the huge baffle that allows the radiation to get in. We can see the radiator panel where the instrument can radiate away the heat, and it's on the famous side that is not impacted by the solar radiation. And we can see as well some boxes which are the electronics. So the IRS is a sounder. The main difference of a sounder with respect to a regular imager is the interferometer. So it's a sounder, it's not an imager, so also what we get as a product, generally speaking, are not images but are interferograms. So this is the telescope. I like to introduce instruments, in this case optical instruments, by showing the path that the optical, the radiation beam has to actually walk in order to get to the detectors. And since we are 36,000 kilometers away, that's quite a long way. So another thing that I like about this picture is that depicts the main elements that are key in order to acquire these interferograms, which are the scan mirror, the calibration and obturation mechanism, the interferometer assembly, and obviously the cold optics, so the detectors right at the bottom. So all this bouncing on the mirrors, this is clearly needed in order to get to amplify the radiation and to get the interferograms. And in order to basically get the radiation from different points of the Earth, we have a scanner. The scanner has this mirror, the M0 mirror, which is the scanning mirror, which is oriented, it can be oriented in the north, south, and east, west directions, and it's a flat mirror, double gimbaled. Then we have a calibration and obturation unit, which once the radiation is acquired, it allows, let's say, to deflect the optical beam or to put in the middle other elements that are needed for the calibration. So in general, this calibration and obturation unit, which is a flipping mirror, so it's literally a mirror that flips, so it either allows the optical path to be undisturbed, or it can put an element which is the black body for black body calibrations, or deviates the radiation to the deep space, which is basically an additional baffle that the instrument has, which is pointing in this approximate -y direction, which is free from other sources. So that is looking at the deep space. And then, let's say, the star of the instrument is the interferometer. The interferometer assembly consists of the interferometer optical bench assembly, which is an interferometer, which has the beam splitter and the hollow corner cube virtual reflectors, the metrology laser, the receiver assembly unit, and obviously the control electronics. So this is basically where, let's say, the magic happens. So this is what allows us to see the atmosphere in the vertical direction. So we have this corner cube mechanism that moves one of the mirrors that allow the deflection of the beam, and by moving at a constant speed and direction back and forth, basically allows us to split the frequency, and the laser allows us to know the exact optical path difference, and the RAW is basically the detector of this information. It's the IRS, it's in the infrared, so in order to provide best products, the detectors needs to stay in a cryogenic environment. So everything that is the cold optics is inside a cryostat, which is kept at a temperature of 52 Kelvin, so it is extremely cold. And ultimately, this is what a detector looks like. So the IRS has two detectors, two retinas, one in the long and the other one in the medium wave infrared, and it's composed of 160 by 160 super pixel arrays with a pitch of 90 micrometers, and each pixel, each super pixel has a subpixel 3 by 3. So this what you can see is a representation of what the detector is seeing, and this also is the field view of the instrument, which we call well. So a regular imager nominally acquires images as per swaths or imaging lines. In this case, for the IRS, we have dwells. So what do we do with the IRS? So that's what we do. So we acquire each dwell, one by portions of the full disk. So nominally, we can identify 4 different areas, which are called LUCs. So LUC stands for local area coverage. And these areas cover approximately 1/4 of the full disk and are acquired in a specific sequence. So for the IRS, we have these repeat sequences in which we acquire the LUCs, and a repeat sequence is called like this because it repeats by reaching its end, and it has a duration, standard duration of 6 hours. And as we can see, we have every 30 minutes the acquisition of what we call a LUC4, which is acquiring the north of Europe. So every 30 minutes we have an image of the north of Europe. The sequence in which each LUC is acquired is it's been analyzed to maximize the visibility of certain areas. We mentioned the repeat sequence as the order in which we acquire these local areas, but what actually provides the instrument with instructions on what to perform is the activity table. So this instrument can perform a number of activities, which are, for example, the commanding of the scanner, the commanding of the corner cube mechanism, and the commanding of the calibration unit via direct commanding coming from the ICU, which is basically the onboard computer of the IRS. And these activity tables contain these instructions by means of offsets with respect to their start. The way the scanner moves is basically dictated by what is called the scan law. So the scan law contains the exact points in which the mirror will point to, and also the motion profile to move from one point to the next. But as you might imagine, the movement of the scanner, but also the calibration unit and of the corner cube mechanism might have an impact on the altitude of the satellite. And for this reason, for each scan law, we need to have also what is called an ABC table. It's a priori compensation, and it basically allows for the AOCS software to compensate the perturbations that are introduced by the movement of the instrument mechanical parts. And this is to guarantee the pointing of the instrument, and we have very stringent requirements on the pointing. This mission scenario needs to update on regular basis. As Enrique mentioned, we need to flip the satellite because we need to keep always the Y side in the shadow, and therefore at some point the instrument will see the field of view upside down. So in order to function regularly, as soon as we flip the satellite, we will have to update the mission scenario, so the scan law and the ABC. So we would have a configuration for winter and summer, and we also have additional configurations because depending on the phase of the life of the satellite, we might be on a different longitude on the orbit. So for example, right after the launch and LEOP, the satellite will be in the west position. During routine operations, then it will be moved central. And then for all the utilization, will be in study-based position, most likely. So we have this 6 nominal baseline mission scenarios. The field of view of the instrument comprises as well wells that are close to the Earth limb. And this might be a problem when we get into the eclipse season. So when the sun finds itself at latitudes in which basically it passes across the Earth and beyond. So for some instance, it may actually be acquired by the instrument. This is clearly to be avoided at all costs because it could cause basically the end of the instrument, the destruction of the instrument, and therefore of the mission itself, MTG at least, not Sentinel-4, but the MTG-S would end like that. Of course, in order to avoid that, we have the failure detection, isolation, and recovery function that takes care of monitoring that the intrusion does not happen, and would react and put the instrument in what is called a wait mode, but that obviously would cause an outage. And since we do provide a service, it is very important that we minimize as much as possible outages, and therefore we need to apply what is called the sun avoidance strategy. So in the sun avoidance strategy, we have our flight dynamics system that has been designed to predict these sun intrusion events. So by extracting this output from the specific function of the flight dynamics system, we can acquire the events, and we can update the repeat sequences and activity tables to perform this skipping of the dwells. So the activity tables will be updated to perform very fast movements over the dwells that are affected by sun intrusion. At the same time, the obturation unit will put the flipping mirror in the black body or shutter position so that we have no radiation getting in. And as soon as we get to the final position and we get out of the risk of intrusion, we can go back to the free beam position and continue with regular operations. We need to calibrate the instrument on regular basis. So not only we need to calibrate the instrument, but also the elements that perform the calibration itself, in this case the flipping mirror itself. So this is another activity that is performed every 6 months right after the geoflip. In this case it's basically the regular acquisition of images with the black bodies, with the difference that in this case the black body is heated by 10 Kelvin. In addition, we need, again, after the geoflip, we need to calibrate the scan encoders. So the position of the scanner, so where the scanner is pointing, need to be known with very high accuracy. And in order to do that, we need to perform this specific activity in which the scanner performs a set of harmonic movements, and by analyzing this, the output of these movements from the science data, we are able to assess whether there are errors in the encoded fingerprint which need to be updated. And if that's the case, this will be done in the frame of the update of what is called the lookup tables. We need also to, this is a little bit on the high end of complexity, but another way that we have to calibrate the instrument is by taking images in deep space, but in a specific well that reside in the deep space alongside the Earth limb. And this also, the characterization of this front section activity is basically achieved by using this specific DS2 and by using dedicated activity tables, which basically there's more frequent acquisition. By on demand, we need to decontaminate the instrument. This means that we just need to heat it, because in a cryogenic environment, there's obviously the chance of having ice particles being formed, especially right after the launch. So, for example, the decontamination is one of the very first activities that is performed at the beginning of the commissioning. And the decontamination consists in increasing the temperature of the cryostat. Obviously, in this case, the detectors are off together with other units, so this activity is performed in a mode of the instrument that is very low. Last but not least, we need to calibrate the laser. As we mentioned before, the laser resides inside the interferometer, and it's basically the laser signal that allows to identify the OPD, but the power that is needed to the laser might change over the years, so it might be needed that additional power is provided in order to get the same performance of the laser. And this is assessed on ground by analysis of the parameters related to the laser, and there is a specific procedure that we need to perform in this case. That was like the overview of all the activities pretty much that we will be performing on the routine activities of the instrument. And all this is basically to get this set of incredible new products on the geostationary level. So here you have, for each detector, the complete list of what the IRS will provide. So this upper and humidity fields in the 3D and the 4D, the 3 wind fields, upper temperature, upper humidity, the ozone, sea and land surface temperatures, fractional cloud cover, the cloud top pressure, air quality ammonia, and atmospheric instability parameters. So this is quite, I mean, coming from working on images, I can't wait to see this at work. And this concludes the presentation.
Perfect. So I can also play. I also get to play with this one. So, I don't know if there are questions from the public. I imagine you're all very, let's say, tired as well, probably. I will start with the, was behind the microphone. Thank you.
I was just curious, given the geometry of the orbit, so geostationary, and the fact that you see Europe like at high latitude, does the instrument have any degradation of the measurement for higher latitude? So in Sweden you get bad quality data with respect to Italy?
No, I mean that is taken into account at the data processing level. So it is something. I mean, I'm not aware of any degradation of the data that is due to. I mean, definitely, what is to be right, but it is taken into account when processing the data. So the algorithm takes care of that. Don't ask me how, because no, the requirement is to provide the same level of accuracy at all.
Say that if there are some, let's say, advantage, of course, the LEO satellite, they can pass directly overside, they have a better view. But the advantage of the geostationary satellite is to have the entire picture, is also to reconstruct better the dynamics. This is in part paid by the angle of view, but as Claudia said correctly, in the specification, the accuracy is say, organized in a way that is already sufficient for those view angles. And of course, it's even better for the area of the equator, which is more orthogonal.
There is a dedicated department, which is the INR. Navigation and registration, that is basically focused exactly on that part.